Another day, another story. The Event Horizon Telescope, EHT, has achieved a decades-long astronomical goal by capturing the first image of Sagittarius A*, the supermassive black hole at the center of the Milky Way. This achievement is a crucial step towards a new understanding of black holes, gravity, and spacetime. This is not the first black hole image captured by EHT, as they had previously revealed the iconic image of M87** in April 2019. However, the capture of Sagittarius A** is particularly significant as it is located in the center of our own galaxy, and is the still point around which the Milky Way revolves. For years, scientists have believed that a supermassive black hole existed at the center of the galaxy, but were hesitant to confirm it outright. The recent Nobel Prize in Physics awarded to Reinhard Genzel and Andrea Ghez for their work on Sagittarius A** further solidifies the existence of this mysterious object. The Event Horizon Telescope, EHT, has used a technique called Very Long Baseline Interferometry, VLBI, to capture images of the shadow cast by the black hole, Sagittarius A**. VLBI combines radio observatories located on different continents to form a virtual telescope the size of the Earth, allowing for the highest resolution in all of astronomy. In April 2017, EHT aimed this virtual telescope at Sagittarius A** and other supermassive black holes. The team captured raw data for the Sagittarius A** image during this campaign, but it took much longer to convert these observations into an actual image. Black holes are not visible as they trap everything that falls into them, including light, but they warp spacetime around them so much that they cast a shadow, which is about 2.5 times larger than a black hole's event horizon, which is the boundary and defining feature of a black hole, the line in spacetime through which nothing that passes through can ever return. The captured image is a dark ring framed by 3 shining knots of trillion-degree gas, which the scientists hope will help them understand the properties of the black hole, the warping of spacetime, and the behavior of other objects in the vicinity of the black hole. The constant changes of Sagittarius A** made it difficult to capture a clear image, but it also makes it an exciting subject for future studies of black holes and Einstein's general theory of relativity. While scientists already knew the basic measurements of Sagittarius A** such as its mass, diameter, and distance from Earth, the *ability to watch it evolve in real time as it feeds on matter provides a unique opportunity to study black holes in a way that was not previously possible. Unlike M87**, the black hole at the heart of galaxy Messier 87, matter orbits Sagittarius A** so quickly that it changes minute to minute, making it challenging to capture a clear image. Here is the extracted image of Sagittarius A. Extracting an image of Sagittarius A** from the data collected in the 2017 observing run took several years. The team of scientists hope that the captured image will help them understand the properties of black holes and the warping of spacetime, and also help them understand the behavior of other objects in the vicinity of the black hole. Scientists first began to suspect the existence of a black hole in the heart of the Milky Way in the early 1960s, following the discovery of active galactic nuclei in other galaxies. The existence of these bright regions at the cores of some galaxies suggested the presence of supermassive black holes. English astrophysicist Donald Lynden Bell argued in 1969 that these black holes were present in the hearts of spiral galaxies, including our own, but were dormant. In 1974, American astronomers Bruce Ballack and Robert Brown used radio telescopes in Green Bank, West Virginia, to discover a dim speck at the center of the Milky Way that they suspected was the galaxy's central black hole. They named this speck Sagittarius A**. Over the next 2 decades, radio astronomers gradually improved their view of Sagittarius A**, but were limited by a lack of suitable telescopes, relatively primitive technology, and the difficulty of looking into the galactic center. The black hole, Sagittarius A**, is concealed by a multilayered veil of the galactic plane, a scattering screen and the obliterated matter surrounding the black hole itself. These layers make it difficult to see through, and that is why scientists used VLBI to capture the image of the black hole. The VLBI allows to see the black hole by using shorter wavelength light. This was a major technological challenge, but it was achieved successfully to have a closer-in views approaching the black hole's event horizon. In addition to VLBI, astronomers using other techniques also contributed to the discovery of the black hole at the center of Milky Way. In the 1980s, physicist Charles Townes and his colleagues observed that gas clouds in the galactic center were moving in a way that could only be explained by the presence of an unseen massive object. In the 1990s, Ghez and Genzel began tracking the orbits of giant blue stars in the galactic center, and mapped their motion around a heavy but hidden pivot point, providing further evidence of the existence of a supermassive black hole. During this time, the situation for radio astronomers also improved. In the late 1990s and early 2000s, new high-frequency radio telescopes came online and could be used in VLBI observations at the microwave frequencies thought to shine from the edge of Sagittarius A's shadow. The advances in computing technology also greatly increased the amount of data that each observatory in a network of radio telescopes could record and process. In 2007, a small precursor of the EHT used a trio of telescopes in Hawaii, California, and New Mexico to make an observation of the veil surrounding Sagittarius A*. While they were not able to create an image yet, they were able to see something that would be vital for future observation and discoveries. Top of form. Scientists had known for some time that under certain circumstances, a black hole would cast visible shadows. The first official meeting for the project took place in January 2012 and the Event Horizon Telescope, EHT, project was established. 5 years later, the EHT team, consisting of over 200 scientists from 8 different observatories around the world, took the first realistic shot at capturing the shadow of Sagittarius A*. In April 2017, the team used telescopes in North America, South America, Hawaii, Europe, and Antarctica to gather 65 hours of data on 1,024 8-terabyte hard drives. These were shipped to supercomputer banks in Massachusetts and Germany for correlation. And after 5 more years of processing and analysis, the team was able to successfully capture the image of the black hole, an achievement that they have been working towards for years. Thanks for watching. Don't miss out on exclusive content, behind-the-scenes footage, and early access to new videos. Subscribe to our channel now.